So let's go ahead now and we'll do the multiplication of the mantisas. So I'll get rid of my image here just to stop the clutter. Now we're going to have to take the output from for the exponent for our value over y, and we're going to have to take the output for the mantissa for our value over x. Now if we were to have a look at the original diagram here, we can see that between this point here, big MX, we have this 1 dot small mx, and big My is a 1 dot small my. Now as I mentioned in the video when I described this, between this section and this section, what we do is we add on our hidden bit. So both of these inputs are assumed to be normal numbers, so the hidden bit is going to be a value of 1. So we're going to have to change the 23-bit mantissa to a 24-bit mantissa, and the extra bit is going to be a value of 1, and then we're going to do the multiplication. So let's go ahead and we'll do that now. So in order to add the bit on, we're going to have to bit extend. So I'll move this up a little bit, gives a little bit more space. So if you head into the bit extender, so it's under the wiring section, there's a thing called the bit extender. So you can click on that bit extender, and we can change this from our 23 bits to 24 bits. So that's going to be 23 bits in, and we're going to have 24 bits out. Now the value of the bit is going to be chosen by some input. Now we could put a 1 there, and we could choose the value of the input as a 1, but we'll put it actually as an input. Okay, so the value, the extra bit that comes in, the 24th bit, is going to be the highest or the most significant bit, and it's going to be given by whatever comes in this input here. So again, we just want to make sure we put the value of 1 in. So we can take a constant, I'll just copy that one here, we'll place it there, and it's going to be an bit value that comes in, so it's just going to be a single bit, and it's a value of 1, and it's already set there as a value of 1. And I'll copy this, and we'll do the same for the x value. And this is us just extended the bit, so relatively straightforward here in the Logisim tool. And then once we've extended the bits, we're then going to go through the multiplication. So again, we'll just use our multiplier here, and this is going to be the input here and input there. So now it's going to be a 24-bit multiplier because we've now extended it to 24 bits. And you can see here we're going to get an output here, which is going to be the 24 least significant bits that come out here, and the 24 most significant bits that are going to come out in this section here. So let's go ahead and we'll actually look at these in our Excel VBA tool. So the first thing we'll do is we'll put in a probe. So we'll just grab one of these probes here. Control C, Control V, just to make sure you understand what we're getting out here. And we'll change this to the actual binary value. Okay, a bit cluttered here, but it doesn't matter, it's only just temporary, just till we see what's happening. And we'll Control V, and we'll face this north. Okay, so this is going to give us the top 24 bits, or the most significant 24 bits of the multiplication, and this will be the 24 least significant bits of the multiplication. So let's go ahead and we'll have a look at this in the spreadsheet. So I'll open it up again and I'll just run through in fact I don't need to run through the multiplication, we already have it here. So we're going to have the top 24 bits, so that's really these 24 bits here, so that's to here. So this here is going to be, the top 24 bits is 1, 0, 1, 0, 1, 1. You can see here 1, 0, 1, 0, 1, 1. And then the other 24 bits are going to be the least significant bits. So the least significant bits are going to run from, if we get to the 24th bit here, so it's going to run from here, so it's going to run that point, so it's going to go 0, 0, 1, 1, 0, 1. Now you can see 0, 0, 1, 1, 0, 1. Okay, so that's just models exactly what we've got in the Excel spreadsheet. So let's go back and we'll continue with our design here, and we can get rid of these because we know what's coming out here. Now if we head back into the drawing here, now this is the part of the drawing that wasn't completely defined here within the drawing, meaning there's little sections missed out. So the output here at this point is a 48-bit number, so that's the big long number we've just seen in the spreadsheet there. Now at this point we're actually going to have the choice between the two outputs. So the choice here has to be made, so we have to take this 48-bit and we have to pick the 23 bits, but we have to pick the proper 23 bits. So there's going to be two options here of 23 bits that we can choose. So again, let's go back into the spreadsheet and we'll see those options. So we know that for the mantissa, if the leading value here is a value of 1, it means that in order to normalize the mantissa value, we're going to have to shift the decimal point from this point here up to that point there. And whenever we shift up to that point there, we're going to be choosing 23 bits for our mantissa. So the 23 bits is going to start from this point here. So we're going to go from this point here and we're going to choose, count along 23 bits. Okay, so it's just off the edge of the screen there, but that's the 23 bits there that we're going to choose starting from this position. Now the other option is that if this value hadn't been a 1 and it had been a 0, then we would be choosing we wouldn't be moving the decimal point would be remaining at this point here. So that would mean that in that case the 23 bits for the mantissa would start at this point here. So we'd then be counting 23 bits from this point and not 23 bits from this point. So then for the next 20 option we'd have would be these 23 bits starting from there. Okay, so it means that we're going to have to create those two sets of values. Okay, 23 bits starting from there to the right, or 23 bits starting from there to the right. So let's go ahead and we'll see how we're going to do that in Logisim. So let's see if we can squeeze the last little section here into this diagram. So we'll move this over a little bit and we'll shift our output so that it brings it back in here. Okay, so we want to be able to make the choice between those two mantissa values. Now one of the values is relatively straightforward in order to get. Now if we were to look at the 24 most significant bits, because those are where our mantissa values are going to come from. Now we need to get access to the most significant bit, because the most significant bit, that's the 48th bit, is the one that's actually going to choose whether we use the 135 value or the 134 value for the exponent. So we're going to have to get access to that anyway. So let's see how we can get access to it. So again, if we were to use a splitter, so we head back into the wiring section here and we'll pick up a splitter. Now in this instance here, we're going to have our 24 bits coming out of here. So the splitter is going to be a bit width of 24. But we only want to have two outputs. We're going to have an output which is going to be the most significant bit, and then the other output will be all of the other bits lumped together. So what we can do here is we can make the top one here the value for our most significant bit. So our most significant bit then, actually if I was to head all the way down again, you might not see this, just you got it there off the bottom. We can make this value here the top value, which is going to be a value of 0. So that will be our most significant bit. And then all of the other values will be a value of 1, which will be our least significant bits, which will be the other 23 bits of the mantissa. So it means that we can, by doing this, we can get access to just the one bit that we want, and this is the one bit here, which is the 24th bit. I know it says bit 23, but it runs from 0 to 23, so it's the 24th bit. So we can connect that onto here, and we can take our most significant bit off at this point here. So it means now that we have our most significant bit, and that most significant bit is going to control the multiplexer, which we have up here to choose the correct value for our exponent. So we can connect that directly to there, and that's going to choose the value, which is the correct value there in this instance, is 135. So that means we're now in a position to connect the output of the mux to the final output for our exponent. So we can just connect that into here, and you can see we've got our exponent value, and this is the correct exponent that we were expecting to see. So you can always have a look back at the multiplication and compare these 8 bits and ensure that we've actually got the right exponent value. So let's go ahead and we'll get the correct mantissa. So as we said, we've got two options. So here's one of the options. We can take the output here, which is our top 48 bits, and we can simply put it through a bit extender. So if we head into the wiring section, we've got bit extender, and you can put that down here, and what we can do is we can change this from the 24 bits to the output, which is a 23-bit output. Now what this bit extender does is it chops off the most significant bit. So it takes the 24th bit and just chops it off. So in effect, and we'll see this just in a second if you don't quite understand it, but in effect what's happening here is if we chop off the 24th bit, it's equivalent to taking the output and shifting it actually left by a value of 1. And the final output is only 23 bits. So the final 24th bit, the very last bit, would be shifted into the next position, and it would be chopped off from the most significant bit. So a bit of a mouthful that, but we'll get in and have a little look at this, and we'll see this happening at the moment. So what we'll do is we'll put a probe in. We'll face it south, and that's going to give us access to the actual bit pattern that we're going to be using. So I could take a copy of this, and we'll just, right, so we've got a little copy of that here, so we can use that copy. So we can see here that we've got our bit pattern here, and if you come down here you can see that the 48 bits of our multiplication is this line here, and all we've done here is we've chopped off the most significant bit. So this one bit here is going from a 24 bit to 23 bits, and it's done that by chopping off the most significant bit. So it's disappeared, and it means that the very first bit that comes in is going to be the 01011. So this is going to run 01011. So we're going to have the bit pattern from this point here counting down 23 bits. So that's one of the bit patterns. Now we're going to get the other bit pattern, which is going to start from this point here. So let's go ahead and we'll see how we're going to get this one. So in order to get the other option for the mantissa, we're going to have to use a left shift. So if we head down here to the shifter, and you can see it's already set up as a logical left shift, and it's going to be an 8-bit. So we drop that down, and you can see here that what we want to do is we want to use the 24 bits for our output. So this is the output here. So we're going to take the 24 bits for our output, and we'll take a copy into here. And again, this thing here actually is going to be number of bits. It's actually going to be a 24-bit value. So it's 24 bits, and this value here, this point here, will make the choice. So this will tell the shifter how many positions you're going to move to the left. Now we know we're only going to move the decimal point one value to the left, and that value will be determined by the 48th bit. So if the 48th bit is a value of 1, we'll shift it one value to place to the left. If the 48 bit is a value 0, we'll shift it 0 places to the left. That is, it will just remain exactly the same as the one above, the same as this one here. So let's go ahead and we'll make the shift. So we have to make a choice here. So we're going to have the 48th bit. So this is the 48th bit here. So we want the 48th bit to come down, and the 48th bit is going to tell this shifter to move either one place to the left or one place to the right. But when you go and connect that, you'll get an incompatible widths, because the choice here for the shift is not the right size. So that is, the shifter here is expecting 24 bits coming in its input. So it means it can shift it as much as 24 bits. So in order to get the actual shift value, we're going to have to use the choice here, a value of anything up to 2 to the 5. That is, 2 to the power of 5 is going to be a value of 32. Now if we had it down as a value of 4, we would only be able to move it 16 positions. So you have to be able to move it at least 24 bits. So 24 bits would be encompassed by a value of 2 to the 5. So this thing here is going to have to be extended to a value from 1 bit to 5 bits. So we're going to have to put this again through an extender. So that's the extender here, and it's getting a 1-bit input, and it's going to get a 5-bit output. So we'll put the 1 bit in, and we'll get the 5 bits coming out. So it means then that if we were to put a probe at this point here, you're just going to get the value for your output here, which again will just be a value of 1. So let's put the probe in. I think by putting the probe in, what I've just mentioned there about the bit extension will become more clear. If I face this north, then you can see here that we're going to have our 5 bits, and that's telling it to shift it 1 bit to the left. And if I wanted to move it 24 bits to the left, I would have to have these full 5 bits available in order to get the number 24. So that's the reason why we've got this little extender here. So that's us being able to shift this output here 1 position to the left. And finally, what we can do is we can take this here, and after we've shifted it to the left, we can then go ahead and we can delete off the most significant bit. So again, we're going to grab one of these extenders here, and we chop off the most significant bit. So this will going to go from a 24-bit to a 23-bit. So again, let's have a wee look, and we'll check the output and see we're actually getting what we expect. So I'll grab this probe here and I'll position it at this point here. So that's the actual output we're going to get now. And you see what we've done is we've taken the original input, so I'll actually take a copy of the original input here as well. Just pop it up here and we'll pop the probe up here. I'll just put another probe in here, Control C, Control C, Control V. And we'll change this to our binary value. So that's our original value here. And you can see here that in the first instance here, what we've done is we've just chopped this bit off and we've got access to these 23 bits. So that's one possible output. Now the other possible output is what we've done is we've taken the 24 bits and we've shifted it one bit up. So by shifting it one bit up and then getting rid of the highest bit, which then becomes this bit, we're going to be left with this value here. And this is the correct value that we're looking for. So let's have a wee look at the Excel spreadsheet again, and you'll see that the other option we're going to have is going to be a value starting from the position here, which is 101100. And you see we've got our 1011000. So that's us got the two options that we require for the mantissa. Now what we want to do is go ahead and actually choose which of these two options we're going to use. So let's clear this up a little bit just by getting rid of some of these because we don't really need them. We just put them in just to help us understand what was happening here. So now what we can do is we can put it through a multiplexer and we'll be able to make the correct choice between these two. So again, we'll go and we'll have a little look at our original drawing just so we can be sure that we know exactly where we are here. So this is now going to be a 23-bit multiplexer. So data bits is going to be 23 bits, and we're going to have our choice for our multiplexer as well. And again, the choice for our multiplexer is going to come from the most significant bit of this value here. So what I can do is, rather than have this wire running, well, I'll put the wire in initially first of all, just as to show it actually working. And we'll take our output here, and our final output here can actually then head up to the mantissa value. Okay, now one thing we have to check, make sure, is that we've actually made the correct choice here, because there's a 1 and a 0 and we could have easily mixed up the choices. But the first thing we'll do before we check that is we'll go and have a little look at our diagram here and we'll see what we've done. So we come down here, and that whole section we just talked about is about making this choice. It's about giving these two options. Okay, so now we've created the two options, we're in a position here at this point here where we now choose between the two options, and we choose between the two options from the 48th bit of the multiplication. So let's go ahead and we'll make sure that we've actually chosen the correct option here. So it's telling us that when we multiply these two numbers together, we'll get this number here. So let's just check and see whether it does actually give you as the right value. So if we head into the multiplier and we'll just run up the tool again, and we'll put in our two values, 492.75 and minus 0.7. Now the right value that we should be getting is this value here, so this is going to be our C3, AC7 and our 666. So let's go in and we'll check and see that we're actually getting that value. So you can see here that that's not the value we're getting. The value we're getting here is C3D8E CCC. Now the reason for that is that down here, whenever we've made the choice here, the multiplexer is not set up quite right. So what we'll do is we'll change this here, and we can put in a NOT gate, and we'll face it north. So then it will just actually choose the opposite one, which should be the correct value. And you can see here now we've got the final output as our C3AC7666, which is the right value. So this is us ostensibly finished our first little bit of our design for a multiplier. So that's us designed the core of our multiplier section. Now it doesn't include the facility to deal with subnormal numbers, it doesn't include rounding, and it doesn't include the multiplication by our special values, for example 0, plus infinity, minus infinity, or a number. But it does allow us to multiply together a core set of numbers. So that's all there is for this video. On the next videos we'll extend in this and we'll add in our rounding errors and also our special cases of plus and minus infinity and 0. So thank you for listening. I'll get you on the next video. Goodbye.